Jai Hind students. Students, I will begin with the saying that laziness is your worst enemy and hard work is your best friend. So students, get rid of your laziness as soon as possible and start believing in hard work. It is only through hard work that success can be achieved. Right students? So study as if there's no tomorrow. So with that, let's begin our session. Students, in the previous lecture, what we have discussed was the magnetic effects of current. We have discussed Oerstel's experiment, and then we have discussed right-hand thumb rule. And this rule is used to determine the direction of the magnetic field at a point due to a current-carrying conductor. Isn't it, students? So today we will be discussing the strength of the magnetic field at a point due to a current-carrying conductor. And the current-carrying conductor may be in the form of a loop or it can be in the form of a straight conductor. So, we will discuss Biot Savart Law or Laplace Law. So, it is one of the basic law in magnetism, right? So, basically, the strength of the magnetic field at a point due to a current-carrying conductor mathematically was given by Laplace. And later on, the formula which was given by Laplace was experimentally verified by Biot and Savart. So accordingly, Biot Savart law is also known as Laplace law. Now let's try to understand this particular law, right? So what we do is, let us consider this to be a conductor. As I told you, it can be a straight or it can be curved. Suppose current is flowing along this direction. This is the direction of the flow of current. And let us consider a small elementary portion. Let us consider this to be P and this to be Q. And let us consider the elementary portion to be DL. So DL is the small elementary portion through which current I is flowing in the direction from P to Q. Let us consider O be any arbitrary point where the strength of the magnetic field is to be found, right? This is suppose the center of the elementary portion. Suppose this is M. M is the center of the elementary portion and MO is the line joining the center of the elementary portion to the observation point. Right, students? And also suppose this distance is R. And remember, it is measured from M to O, not from O to M. It is measured from M to O. So, if you represent it in vector form, it will be directed from M to O. This is R cap. Right? And also, let us consider this angle to be theta. This is the angle which is theta. So, what is theta? Theta is the angle which the direction of the flow of current makes with the line joining the center of the elementary portion to the observation point. Right? So, what Biot Savart found or Laplace found was the strength of the magnetic field at point O due to this current carrying elementary portion is found to be directly proportional to the current flowing through that elementary portion. Look students, magnetic field is normally represented by capital letter B. So here at this point we are trying to calculate the magnetic field due to this small elementary portion. So dB represents small magnetic field. B is the magnetic field. B is the magnetic field. So dB will represent the small magnetic field at point O due to the small current carrying elementary portion PQ. So what Laplace or Biot Savart observed was the strength of the magnetic field at a point is directly proportional to the current flowing through the elementary portion. Second, they also found that it is directly proportional to the length of the elementary portion. That is, greater the length of the current carrying conductor, more is the strength of the magnetic field at a point around the current carrying conductor. Right? And they also found that or observed that it obeyed inverse square law. That is, the strength of the magnetic field at any given point near a current carrying conductor varies inversely as the square of the distance of that observation point from the center of the elementary portion. So it obeys inverse square law. And lastly, they observed that the strength of the magnetic field is also found to be directly proportional to the sine of angle between the directional flow of the current and the line joining the center of the elementary portion to the observation point. The distance is to be measured from M to point O. So theta is the angle which the directional flow of the current makes with the line joining the center of the elementary portion to the observation point. Right? So students, what will be the statement of Biot Savart Law? Biot Savart Law or Laplace Law states that the strength of the magnetic field at any given point near a current carrying conductor due to a small elementary portion is first directly proportional to the current flowing through that elementary portion, second directly proportional to the length of that elementary portion, third it obeys inverse square law, that is, it is inversely proportional to the square of the distance of the observation point from the center of the elementary portion under consideration. And fourth one is, it is directly proportional to the sine of the angle which the directional flow of current makes with the line joining the center of the elementary portion to the observation point. Right? So, combining these four, what we get is dV. It is the small magnetic field due to the small elementary portion. It will be I dl sine theta divided by r square. Now students, as we are aware, in order to eliminate this proportionality sign, we need to introduce some constant, and that constant is known as constant of proportionality. Right? Let us represent it by k, small letter k. So what we get is dV is equal to k I dl sine theta divided by r square. Now k is constant. We'll discuss the factors on which the value of k depends, right? You must remember, in electrostatics, k, which is constant of proportionality, it is 1 over 4 pi epsilon naught. Epsilon naught is the absolute permittivity of the free space. Here k is the constant which is known as, or rather which is given by mu naught divided by 4 pi. Here mu naught, it is the absolute permeability. So mu naught is the absolute permeability of free space. It is the absolute permeability of free space. Free space means vacuum. Free space or vacuum. Right? So k is constant, which is given by mu naught over 4 pi. Mu naught, students, it is the absolute permeability of free space. This is naught. So it represents the case of vacuum or free space where there is no medium. Right? Permeability. Actually, this term we will discuss later on, but you need to remember this physical quantity permeability that actually represents the conducting power of a medium towards the passage of magnetic field lines through it. So, a medium having more permeability value means it allows the magnetic field lines quite easily. It has more conducting power towards the passage of magnetic field lines through it. So, students, permeability represents the conducting power of a given medium towards the passage of magnetic field lines through it. So that's the importance. And in case of vacuum, mu naught, its value is constant and it's found to be 4 pi into 10 raised to the power minus 7. This is the standard value, and you need to remember it. For vacuum or for free space, the absolute permeability is given by 4 pi into 10 raised to the power minus 7. Now regarding its SI unit, look students, 4 pi is constant. So K will have the same unit as that of mu naught, isn't it? So let's find out the unit of K. Over here K is dB multiplied by r square divided by I dl sine theta. So SI unit of K is magnetic field. Its SI unit is Tesla. It is represented by capital letter T. It is named after very famous scientist Nicholas Tesla. So SI unit of magnetic field is Tesla, right? Distance square, so it is meter square. Current, it is ampere. dl, it is meter. Sin theta, as we are aware, all the trigonometric functions are dimensionless. So what do you get is Tesla meter per ampere. So students, this is the SI unit of constant of proportionality, that is K. So therefore, mu naught, which is the absolute permeability of free space, will have the same unit as that of K, which is Tesla meter per ampere. So this is the SI unit. So students, please remember this particular value. So mu naught, again I must state, it is the absolute permeability of free space. Permeability represents the conducting power of a medium towards the passage of magnetic field lines. And its value for vacuum is 4 pi into 10 raised to minus 7. SI unit is Tesla meter per ampere. That is what we have derived right now, right? So what will be the value of K then? What will be the value of K then? It will be mu naught over 4 pi. Mu naught is 4 pi into 10 raised to minus 7 divided by 4 pi. So K would be equal to 10 raised to minus 7 Tesla meter per ampere. So students, the strength of the magnetic field due to this small elementary portion in magnitude may be written as 10 raised to minus 7. In place of K, you can write 10 raised to minus 7 and I dl sine theta divided by r square. So this is the strength of the magnetic field at point O due to a current carrying small elementary portion PQ. I'm sure you have understood this particular law, isn't it? So before we start with the vector law, with the Biot Savart law in the vector form, we must discuss some special cases as well, right? So one of the cases, first very important point is, what happens if this observation point lies on the conductor? Suppose this is the conductor. If this observation point O lies somewhere over here, if this observation point lies somewhere over here, then theta would become 0. If theta is 0, then sine 0 is 0. So the magnetic field becomes 0. So students, the point to be noted is that magnetic field at a point on the axis of a current carrying conductor is always 0. Right? Whether it is a thick wire or a thin current carrying conductor, at any point on the axis of the conductor, the magnetic field will be always 0. So this is an important point. So magnetic field at a point on the axis of a current carrying conductor is always 0. Please do this. Do keep this in mind, right? This is very, very important. And second, students, we need to discuss the factors on which the value of K depends. It's same as was studied in electrostatics, right? So factors on which the value of K depends. Okay, first, the value of K, it obviously depends upon the system of the units so chosen. Here we obtained the value of K to be 10 raised to the power minus 7. That's an SI. In case we choose some other system, then the value of K will get changed. So obviously the value of K does depend upon the system of the units so chosen. So it depends upon the system of the units so chosen. Right? Second, here K is mu naught over 4 pi. In case the current carrying conductor and the observation point and the space between them is filled with some medium, then instead of mu naught, we should have written mu, which would have been the absolute permeability of the medium under consideration. So, the value of K depends upon permeability value, and permeability for different medium is different. Therefore, the value of K depends upon the nature of the medium between the observation point and the current carrying conductor. So, it also depends upon the nature of the medium. So students, these are the two essential points on which the value of this K depends, right? It depends on the system of the units so chosen, and secondly, it obviously depends upon the nature of the medium between the current carrying conductor and the observation point. In case of vacuum, it's given by mu naught over 4 pi, which in turn will give you the value of K as 10 raised to power minus 7 Tesla meter per ampere in SI system, right? So now what we'll discuss is, this is the magnitude part. Now we will try to find out the direction of the magnetic field. Yesterday also we have used one rule that is known as right hand thumb rule. Using that rule, we can easily determine the direction of the magnetic field at point O, right? But writing Biot Savart Law in the vector form, in that way also we can easily find out the direction of the magnetic field at point O due to this current carrying conductor. So let's try that. And students, one more thing. In order to find out the total magnetic field at point O to this entire conductor, you need to integrate it. So therefore, net magnetic field would be given by integration of this. You can take out the constant, that is 10 raised to minus 7. So it will be integration of I dl sine theta divided by r square. So this will be the total magnetic field at point O due to the entire current carrying conductor, right? How to integrate it, what will be the limits, that we'll discuss under the topic applications of Biot Savart Law, right? Okay, now we will try to represent Biot Savart Law in the vector form. And the importance of writing Biot Savart Law in the vector form would be that we'll be able to understand the direction of the magnetic field at point O. So let's try to represent Biot Savart Law in vector form. Now look students, in magnitude, the magnetic field is given by mu naught over 4 pi. In place of K, you can write mu naught over 4 pi, right? And obviously we are assuming the medium to be vacuum between the observation point and the current carrying conductor. So the strength of the magnetic field at point O due to this current carrying conductor, due to this elementary portion as per Biot Savart Law is mu naught over 4 pi I dl sine theta divided by r square. Now our main objective is to write this Biot Savart Law in the vector form. And here I must first introduce the term current element. Now look students, current we all are aware, it's a scalar quantity because we tend to add current algebraically using laws of algebraic addition. We don't add currents vectorially, isn't it? So current is always treated as a scalar quantity. Now current element, when the length of this elementary portion PQ, that is dl, when it is measured along the direction of the current, when the length of this elementary portion, that is PQ, is measured along the direction of the flow of the current, then the term current multiplied by the length of this elementary portion, this entire term, is treated as a vector and is known as current element. So I dl, that represents current element. Magnetic field at a point is due to a current element, right? So I dl represents current element. So what will be its SI unit? current multiplied by distance. So its SI unit is ampere meter. This will be its SI unit. So current element is I into dl. Here the length of the elementary portion dl is to be measured from P to Q, that is along the direction of the flow of the current. In that case, current multiplied by the length of the elementary portion will represent a vector quantity, and that is known as current element. So magnetic field is due to a current element, right? So we will make use of this vector quantity while representing Biot Savart Law in vector form. So what to do is mu naught over 4 pi r square. Now look, ideal sine theta, it can be represented as ideal vector cross r cap. This is the vector product or the cross product, and r cap, it's the unit vector. Students, remember, this is r cap. Its direction is from the center of the elementary portion to the observation point, right? We all are aware of the cross product A cross B. It's equal to product of magnitude of A and B, sine of the angle between them, and n cap, isn't it? So, ideal vector, this is the current element, cross r cap in magnitude. It will be equal to ideal magnitude. The magnitude of r cap is 1. The magnitude of unit vector is always unity. And what's the angle between them? Theta. So ideal cross r, it will be like this. So the angle between them is theta. So A into magnitude of B and sine theta. This is sine theta. So this is what I have done. In place of ideal sine theta, you can represent it as ideal vector cross r cap. Right? This is ideal vector cross r cap. So this is the vector or the cross product of the current element and this unit vector. Now, as we are aware, unit vector is vector divided by its magnitude. So substituting this value of r cap over here, what we get is dB vector. It will be equal to mu naught I dl vector cross r vector divided by 4 pi r cube. Unit vector is vector divided by its magnitude. So it becomes r cube. So this is the representation of Biot Savart Law in the vector form. Right, students? So angle between these two is measured or oriented from ideal vector cross r vector. So it is measured in the clockwise direction as shown in the figure. Clear? So by making use of the properties of the vector product, we know if r vector is given by a vector cross b vector, then r vector is perpendicular to both a vector as well as b vector. So by those properties of vector product, we can safely conclude that dB vector must be perpendicular to the current element as well as dB vector must be perpendicular to r vector. That is, the magnetic field at point O must be perpendicular to both current element as well as r vector. So, in other words, we can state that the direction of the magnetic field at point O is perpendicular to the plane containing current element and r vector. Am I clear, students? So one thing we are very certain is that the magnetic field at point O is perpendicular to the plane containing this current carrying conductor. Isn't it? Now whether it's in the inward direction or in the outward direction, that again can be found by using the properties of the vector product. So here the angle is oriented from ideal vector to r vector. So it will be like this. So thumb is indicating in the inward direction. So therefore the direction of dB vector would be perpendicular and directed inwards. And yesterday we have discussed for perpendicular and inward direction we will represent it by this particular symbol. Right? So yesterday we have discussed right hand thumb rule. That rule also can be used over here to determine the direction of the magnetic field at point O. How to use that rule? Current is flowing along this direction. So let us grab this current carrying conductor in the palm of our right hand such that the thumb points towards the direction of the flow of current. In such a scenario, the direction in which the fingers curl, that will give us the direction of the magnetic field. So in this case, at point O, the magnetic field lines will enter like this. It will enter. So at point O, the direction of the magnetic field would be given by drawing a tangent directed inwards. So what would be the statement? The magnetic field is directed perpendicular to the plane of the whiteboard in my case and directed inwards. That is what we have obtained the result by using the properties of vector product as well. So both are in obviously agreement with each other. Whether make use of the properties of vector product or you can make use of the right hand thumb rule. Clear, students? So this is the proper representation of Biot Savart Law in vector form. Here I must mention very important essential point of difference between electricity and magnetism. Now look, student, electric field is due to an electric charge which is a scalar quantity, while on the other hand magnetic field at a point is due to current element which is a vector quantity. This is a very essential point of difference between electricity and magnetism. Another very important point. Look, electric field is represented by electric field lines which emanates, originates or starts from the positive charge and terminates or ends at the negative charge. While on the other hand, magnetic field, which is represented by magnetic field lines, they are in the form of continuous closed loops. They neither have starting or emanating point, nor do they have any end or terminating point. They are in the form of continuous closed loops. So these are the two fundamental differences between electricity and magnetism, right? So students, I hope you have understood this topic of Biot Savart Law, and please do study well. And in the next lecture, we'll start with the applications of Biot Savart Law. There are 3 or 4 applications along with different and several numericals based on it. So we'll discuss those topics in the coming lectures. So do join me in my next lecture, right? Thank you.